So now we are talking about the universal Turing machine. Till now we have seen the Turing machine, and in this case we have seen that you can have some algorithm and you have the Turing machine to execute the algorithms. So you are having some problem, and for that problems you can devise some Turing machine that can execute the algorithm for the problem. Now, if you think that if you have some different problems and if you want to solve some different problem or you want to compute some function, then again you have to go for different Turing machine that can execute your algorithm for the different purpose. So every time you have some new problems, for that actually you have to go for the, again you have to construct the new Turing machine for that. And the same thing is earlier also, once before the 1936, when the stored program concept was not there, at that time also, if you want to solve some more, if you want to do the calculation in different manners, then you need to, you were required to rewire again. So during 1936, once the stored program concept comes, and Alan Turing has discussed the abstract model of computation, then actually we, in the memory, we are usually begins with storing the programs, or you have the data in the memory, and your computer is supposed to process the data. So in your modern computer, you can use you can use the computer for solving different problems. Means you have the different algorithms, and with the help of your computer you are able to execute the different algorithms for the different purpose. Means your computer is able to execute all your algorithms along with the input you are supplying to the algorithm. So see, this is actually we need in case of the Turing machine. So when we talk about the universal Turing machine, then what we mean that in your universal Turing machine should take the input as the Turing machine, and the input you are supplied to that Turing machine, and on behalf of this input, your Turing machine, universal Turing machine, is going to simulate the action of your ordinary Turing machine. So actually we are simulating the computer like these things, like we have the universal Turing machine. Okay, we denote the universal Turing machine by writing TU. So whenever we have the universal Turing machine, what we need, this universal Turing machine should be able to execute the Turing machine, different Turing machine on the input, whatever your input you are supplying to those Turing machine. So here actually we have the universal Turing machine, and we want to execute your Turing machine for the input. So you can say that your Turing machine T may be given the input Z, and the job of your universal Turing machine is to simulate the action of the T using the input Z, and whatever be the output, it is going to produce the output on result of the given input. So this actually we need, and for that actually, just like we have the computer, we have the whatever programs you are going to write, whatever variables names you are given, and we need some fixed symbol, and using those symbol you can represent the Turing encoded version of the Turing machine. So actually for discussion of the universal Turing machine, we need to discuss the encoding system, so that you can encode the Turing machine you are supposed to execute on the given input. So you have the Turing machine which you need to encode, and also you need to encode the input. So actually your input of the universal Turing machine is the encoded form of the Turing machine along with the input you are going to supply. And your universal Turing machine simulates the processing of Z. The job of this universal Turing machine is what? It is going to simulate the processing of the input z by t. So you are going to process the input z by the t. So you are supplying the input z to the t, and you are encoding the Turing machine, and you are also encoding the input, and this encoded string you are going to supply to the universal Turing machine, and here whatever output you are going to receive, this is the encoded form. The output is in the encoded form. So this is the notion of the universal Turing machine, where we want the Turing machine to execute the our different Turing machine for different purpose you might have constructed, and for the input there you are going to supply on those Turing machine. So question is that what we need actually, we need to find out the encoding of the Turing machine, how we can encode the Turing machine, and also how we can encode the input. Now for encoding the Turing machine and encoding the input, actually we also need that, okay, there must be some fixed finite set or fixed infinite set from where actually you need to take the symbols for writing the names of the states or for writing the input name of the input symbol. Like we have in the in case of the computer also, we have some fixed character set, or you have the rules for writing the name of the variables or identifiers. Here also you need some fixed infinite sets to take the state names, and also you need some fixed infinite set for the tape symbols. Why actually you need for that? It is because you might have the two machines, and if you have the two machines, they are taking the say the symbols A and B, and some other machine you may have which takes the symbol A and C. Like different students is going to write the programs. Even you are writing the program for the same purpose, but different students may write the identifier names differently. So somebody has given the name this, and somebody has given the name this, somebody has given this. So somebody has the input symbols maybe AV, some input symbols maybe someone has taken the input symbol A and C. So if you want that these two Turing machines are different, then you have to give the different codings to these symbols. So that's why actually we need some fixed infinite set from where you can take the name of these tape symbols, from where you can use the tape symbols, and also we have some fixed infinite set from where you can take the state names of the Turing machine. So let us see that we have, okay, so let us see we have some two fixed infinite set. One is, I'm writing like this. This is the Q in some different style, and say I'm having this set and state name we are taking from this set. So Q1, Q2, like the things. Okay, you can take. And we need other infinite sets which from where we can take the tape symbol. Say this is the A1, I can say this is the A2, and then and so on. So if you need the state name for constructing your Turing machine, if you want the state name, you can take from this set, and also if you want to take the name symbols, you want to use the symbols for the tape, you can access this set to take the tape symbol. So these are the two fixed infinite set we have. So if you have the Turing machine T, say if you have the Turing machine T, which is Q, sigma, tau, q0 and delta. Let some Turing machine T is there, and then what we need actually, whatever be the set Q, the elements of set Q are taken from the set Q. Okay, so actually you can say that Q is subset of the set Q, which is written in some, and this Q is, and this is different. So this is it contains many symbols that you can take for the state name. Out of these symbols, you have some symbols, some elements in the set Q. Also, we have the tape symbol, and this tape symbol is also the subset of the set Q. So for constructing the machine, for giving the name of the state, you can take the elements from this set, and for giving the tape symbols, you can access the element containing in the S. And this is the condition. So how question is that first you need actually to associate these state name, and you need to associate these very tape symbols in some string. So actually we assume here that in the universal Turing machine, we can encode the Turing machine along with the input, where we have the two symbols in the universal Turing machine. We need here, we have only 0 and 1. So we have only 0 and 1 in this case. So whatever you have the encoding version of the Turing machine, you have the string of 0 and 1s. Encoding version of the input, you have the string of 0 and 1. So you have the long strings of 0 and 1. So this is the input you are going to supply. So we have the two symbols. We are having the two symbols in the universal Turing machine, assuming that one is 0 and other one is the 1. So now actually you need to learn what should be the encoding, what should be the encoding function, so that you can encode the Turing machine and the input to supply to the universal Turing machine. In fact, there are a number of encoding mechanism available. We are going to learn one coding scheme here. Show how we can encode. We are going to learn the encoding function. Encoding function for that. Let we denote the function by writing E. So first actually we need to associate the string of zeros and to the name of the states, to the name of the tape symbols, and to the name of the directions of the tape head move. So tape head is also one output. You know that once you are going to simulate the moves, then your Turing machine may move the tape head to the left, right, or it may keep stationary. You need to encode all such things. So how you are going to encode? So first you see that we are going to associate all such things with the string of zeros. So we are going to associate the state names, tape symbols, and direction of tape head moves. Direction of tape head moves to string of zeros. So we are using only the zero symbol. So we have to use only two symbols. One is 0 and 1, because your universal Turing machine understands the two symbols 0 and 1. So how we can associate this? So first you can see that we have the halt state. So you have the halt state. So how you can associate the halt state? How you can denote the halt state with the string of zeros? So we have the halt state, and let us use this as, this means that you are associating the halt state with the string of 0. So you have 0. We can write single 0. Once you write the single 0, this means you are denoting the halt state HA. Then whenever you are having the HR, we are using the double 0. So once you encounter double 0, you mean that, okay, this is the state HR. Whenever you are having these are the halt state, you can have other states also. So associate the other states Qi by string of 0 I plus 2. Why I plus 2? Because 2 0 is for the HR. Then if you have the Q1, then 1 plus 1 means the state name, the non-halting state names start with the 000. So this is for each Qi which is in the set Q. Now, so this is what? This is the state name you have associated. Now you can associate the tape symbols. So tape symbol, blank, how you can denote the blank symbol? Blank symbol we denote by writing 0. Then you may have any other tape symbol. So you can say AI. So how you can represent the AI? With the string of zeros, I plus 1. And this is for each AI which is taken from the set S. Okay. And you have considered the strings of zeros for the tape symbols. Now you can go for the directions. So here we associate the stationary move with the 0. Then you have the left direction move. We can write as 00, and for the case of movement of the right side, you can denote by writing 000. So this is the strings. You have associated the strings of 0 for the state name, for the tape symbol, and for the direction. Now you might have the question that you are denoting the 0 for halt state HA. You are also denoting the 0. You are also representing the blank symbol using the single 0, and you also represent the stationary move, stationary direction with the single 0. So how your computer would know that whether you are specifying the halt state or whether you are specifying the blank symbol or whether you are specifying the stationary move. Similarly, you might have the 20, as you have given the 20 for the left direction move, and here you have given the 20 for the halt state, which is the rejection. So how would your computer knows that whether this 20, and how your universal Turing machine come to know that this 20 is for the HR or this 20 is for the left side direction move? So no problem. Your universal Turing machine will understand very easily whether you are using the single 0 for the HA or whether you are using the single 0 for blank symbol or whether you are using the single 0 for stationary move. How Turing machine is going to identify this? By using, see, we are going to encode now the moves. So what is the move you have? Move means, so how you are going to make the moves? So like this, we have the moves in the form of the so you can represent the moves like this. So your Turing machine is actually consists of what? Number of moves. So assuming that we have some moves in the Turing machine, which I'm going to denote by writing M means moves. You may have some ith move or nth move. So this, you are having the P and you have some symbol here, like tape symbol you may have, say for example A. And once you are having this, you might have the output like this. You are going to the state q, and q, you know that q can be any non-halting state or halting state, and you can have any tape symbol. A and B can be blank also, there is no issue. And here is what? This is the direction of the move. So this is the move. Turing machine, in the Turing machine, we have the move, which is the 5 tuple U. So move is having the 5 tuple. First one is what? This is the current state of your Turing machine, and A is the symbol which is scanned by the tape head position. The tape head is scanning the square containing the symbol A, and A can be blank or A can be any tape symbol. Then the third one is also the state, but this state is what? Your machine is transiting from P to Q, and possibly this may be the halting state also. And B is what? B is the tape symbol, that is the modification of A. You are replacing A with the B, and D can be any directions, either left side, right side, or stationary. So how you can encode this move of the Turing machine? So for encoding the move, we are having the encoding function E. How you can encode? So see, we are encoding the move of the Turing machine. So say this is the AM, then this move is AM. So we are encoding this move. How you can encode? So first one is what? This is the name of the state. So we have associated the state name with some form of 0. So you have the state name, and which is the Q. And now we are going to separate by 1. Okay. Then we have this is the tape symbol. So we have associated the tape symbol with some 0. Then we separate by 1. Then we have the state name again. So you have some string of zeros for the S, for the state name Q. Then you are going to separate by 1, and you have some state name, some string of zeros for the B also, and then you separate by B, and you have some encoding string of 0 for the direction. So you are having the direction D. This. So now this is the encoding of your move. So what you have learned that. So this first is what? This is the name of the state, your current state of the machine. This move says that this is the current state of your machine. Okay. So this is your current state, and the tape head is scanning the symbol A, which is A. How would you know? See, the state name, we have associated the state name with the string of zeros. So you will have here you have the only string of zeros, and this string of 0 is separated by 1. So you are separating by 1. Then you have the next tuple is what? The next tuple, this is the name of tape symbol, and in this also you have the string of zeros only. Tape symbol you have associated with the string of 0. So this will be separated by the 1. Then again you have the state name, which has only the string of 0. Then you are also again separating by 1. Then you have the name of the tape symbol here, separate by 1, and directions, then separate by 1. This means what? Now actually your move is having the pattern. This is the 5 tuple, and this is the pattern, particular pattern. Now you easily come to know that whatever you have in mind earlier, that how you would know that whether single 0 is for the HA or blank symbol or S. Now your universal Turing machine will uniquely identified because of this, as this is the pattern. Move is the pattern in the fixed ordering. You have the order. So this is the ordered 5 tuple you have in this case. The first one, your Turing machine knows that the first one is the name of the state, so that once it finds the string of zeros here, it assumes that okay, this string corresponds to the name of the state. Then once you go for separating by 1, then here it comes to know that the second tuple is actually the name of the tape symbol. And then once you separate by 1, then Turing machine says that okay, yes, this again, this is the name of the state. And then once you separate by 1, then Turing machine knows that okay, yes, this is the tape symbol, and finally Turing machine knows that this is the last tuple, and last tuple is corresponds for the direction. So this is the direction. So in this way, even you are using the same number of zeros, Turing machine would uniquely identifies that whether it is for the state name or whether this zero of string of zeros for the tape symbol or for the direction of the tape head moves. So in this way, your Turing machine identifies the pattern according to the pattern, 5-tuple patterns. It identifies what is the current state, what is the current head positions symbol, and what is the result of this transition function. So here this is the input of the transition. This is up to here. This is the input of the transition. Okay, and the output of the transition function is given in the next 3 tuple. So this is the output of your transition function. So this is the way you are going to encode. Now when you encode, actually, then Turing machine is what? Turing machine is nothing. It is consist of the number of moves. So Turing machine may have the, whenever you are having the Turing machine T, so Turing machine, actually encoding the Turing machine T means you are having the number of moves in the Turing machine, and you have to give the encoding of every moves. So assuming that Turing machine T contains k moves, so you can say that M1, M2, and you have the mk moves. So Turing machine consists of the moves. So you have the k moves in the Turing machine. So in a TM. So if you have the k moves in the TM, then how you can encode the T? So you are going to you can encode the Turing machine T. Encoding the Turing machine T means you are encoding the moves. Now move M1, which one is the M1, which one will be the M2, which one will be the MK. This is not, in this case we don't have any ordering. Actually you can give the move, any move to the say first move you can give any at the beginning. Once you start, you may give that move 1, and once your Turing machine last goes to the halt state, you may give the move as mk, last move. So it is not necessary. Also the last move for which your Turing machine halts, actually you can give m1. So m1, m2, mk, you can give in any ordering. The order is not important actually, and your universal Turing machine will automatically find out what is the correct move of the Turing machine T. So no worry, you don't require to make any ordering. You can go for some arbitrary orders of the moves. So you can encode the Turing machine mentioning some arbitrary orders. So you don't have any some fixed ordering in the moves. So encoding this means you are encoding the moves, and hence actually how you can separate the move. So you are encoding the move m1, and you have to separate by 1. So now you come to know that your Turing machine come to know that yes, now you are going to, after you are getting 1, your Turing machine goes for the next move. So you are having the m2, then your Turing machine goes for the move 3, and so on, and finally your Turing machine goes to the move mk. You are encoding the mk. So what you have seen, you have encoded that move like this. So at the last of this move you have the 1. You know that at the last, once you have the encoding of the move, the last symbol of the move, actually what is this? This is 1. And here what you are doing, so this is the encoding of move 1, and here you have the last symbol as 1, and then again you have the 1. It means you have the 2 ones. So once your 1 move completes, then you will find the 2 ones. Your universal Turing machine will come to know that when your universal Turing machine identifies the 2 ones, it comes to know that okay, yes, I'm now, the move is end, and now I'm going for the next move. So every move, actually in the encoded version, is separated by the double one. So move is separated by the double one you have. So that's why this is the so you have this kind of situation, and then you have the input. So how you can encode the input, like you have the input Z, and that Z has the, you may have the key symbols. So you can say Z1, Z2, and Z key. So you have the key symbols. Z consists of the key symbols, means length of Z may be key. So how you can associate the, you can encode the input. So this is the input actually. You are going to supply the input to the Turing machine, and you are going to encode the input inside. So how you can encode the input? So encoding means you have to give, say you are writing at the beginning 1 and then EZ1. You know that this is the tape symbol, whatever the string of zeros here, then separate by 1, and you will find the other tape symbol, say Z2. Then so here actually you are associating the zeros to the tape symbol. So you have the SJ1, right, and here you have the SJ2. So this is the first. So here you have the string of zeros, here also you have the string of zeros, then separate by 1, and so on, separate by 1, and then you are having the string of zeros to the Z key. So Z key, right. So now see, this is the encoded form of the input. So you have associated with the tape symbol with 0, associated the tape symbol with zeros, associated the kth JK tape symbol with ZK tape symbol with zeros, and you are separating with 0. And you can remember that at the beginning you are having the 1. So why it is 1? Because once you supply the Turing machine, the input to the universal Turing machine is what? Input to the universal Turing machine. Universal Turing machine is actually string of zeros and 1. So what is this? You are going to supply ET and EZ. This is the composite string you are forming. So ET EZ. Now the question is that how your universal Turing machine, how the universal Turing machine will come to know that, how it would come to know that where is the end of the moves and where is the input. Okay. So in this case, EZ, you have known EZ starts with 1, and once EZ starts with 1, then you are having what? This is 1, and you know that if you consider the move T, so move itself contains, like EMK, it contains the last symbol as 1, then this is again 1, you have the 2 number of 1s. Now when you concate with the ET to Z, then you have 1 again, means you have the 3 number of 1. So when your universal Turing machine comes to know that you have the 3 number of 1, so you have 1, 1 and 1, then it comes to know that yes, after the 3 number of 1s I have the input here. So it identifies that what is the input you are going to supply to the Turing machine T. Now how your Turing machine actually, universal Turing machine comes to know that what is the current state, from where I have to start, means what is the initial state. So once you are going to give the encoding, then you can say you have to mention in the encoding, so let Q is the initial state. So if Q is the initial state, then how you can encode this Turing machine? If this is the Q is the initial state, then encoding of the Turing machine T. So encoding of T is actually what? You have the first at the beginning, you have the initial state, and now actually you are going to separate by 1. So whenever you are having the initial state, okay, you are going to separate by 1. So now the task is over. So actually your universal Turing machine is getting the input like ET and EZ. Now ET is what? ET is what? ET contains the sequence of moves. Okay, means it may have k moves, and in this there is no particular sequence. Actually your ET will have the encoding form of the number of moves in any order, in any arbitrary order. And at the beginning, you are going to provide the initial state of your Turing machine T, so that your universal Turing machine will come to know that at the beginning of the encoding at the beginning of the encoded form of the Turing machine T, it comes to know that, okay, this is the current state. Okay, so this is the way. So this is the encoding form of the, you are going to give the encoding, right? And this is important actually. You have. So see, actually universal Turing machine is going to have the input like this. So in your universal Turing machine, okay, so your universal Turing machine, we have the TU, we done it by writing the TU. So you are having the TU, and your universal Turing machine, this TU is going to obtain the input which is in the encoded form, ET and EZ. And then finally, TU job is to simulate the action process of the Z by T, and whatever be the result of this, it is going to produce, and it is in the encoded form. So this is the string you are going to supply. So this universal Turing machine is given the encoded form of the Turing machine and the input it is going to take, and the job of your universal Turing machine is to simulate the action of the Turing machine on the given input, and whatever is the result, it is going to produce the the Turing machine, universal Turing machine is gives the encoded form of the results for the results on the given input. So this is one encoding scheme we have seen. So here we are having the encoding scheme where we give only the string of zeros to the name of the state, name of the direction, and tape symbols. And for the moves, we are going to separate the tuples in the moves by ones, and the moves, we are going to separate the moves, different moves in the composite string by double one, and we come to know that the input of given input in the composite string will be after the 3 ones. And at the beginning, we have only the state name, which is the initial state, and after that we have the encoding form of the, once you are accessing the encoded string, composite string at the beginning, then universal Turing machine comes to know that, okay, at the beginning these zeros are correspond to the name of the state, and once it finds 1, then after that it actually understands that, okay, this is the moves. So this is the encoding function. So you can encode any Turing machine in this way, and you can supply to the universal Turing machine, and your universal Turing machine simply simulate the execution of the T by on the given input set. Let us see one example. For the example, we are taking some simple machine. So say we have the initial state. You are the initial state. Q0 is the initial state, and from this you can move. You have the blank symbol. You can move, replace with blank. Go to the right. Okay, then you may go to some state. Let us name the state P. I'm going to the state P, and in this P, what I'm going to do? If I'm having the B, replace with B and go to the R. This is sure. Now, whenever you are scanning and you may have the blank symbol, whenever you have the blank, replace with blank, come to the left. Or you may have the A, assuming that in the Turing machine, in this Turing machine, we have the alphabet, which is A and B. We have the two symbols. So now after B, you may have some A also. So whenever you have the A, you are replacing A with B and come to the left and say you are in the state R. Whenever you are in the state R, so what you are having here? So you have all B's you are going to replace in scan. Then as soon as you are identifying the first A, you are replacing the first A with the B, and you are replacing the A with the B and coming back to the left. So like this, you have the B, B, and A. Say for example, you are given like this. So you are scanning at the P, you are scanning for the B and going to the right. You are going to the right, and right you have the A. You are replacing this A with B and coming back to the left, and you are here. So, and here you are the square 0. Coming back to the here. So what you are having? You have only the B's, okay? So B replace with B and come to the left. And whenever you have the blank symbol, it's the square 0. So whenever you have the blank symbol, replace the blank with blank and you move the tape head stationary and you are going to the halt state. Your Turing machine is going to halt. The question is not that for what purpose this Turing machine is there. Our main job is to understand the encoding function. Okay, this is our main job. So you can have any arbitrary Turing machine, just like. Now see how many moves are there. This Turing machine has number of moves. You can say that this is the move number 1, or you can say this is the move number 1, or you can say this is the move number 1. You can make any node. You can give 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, or you can say this is move number 1, 2, 3, 4, 5, 6. Any order, it doesn't matter. So let us we assume that this is move 1, this is 2, and this is move number 3. This is move number 4 we have, and this may be move number 5, and this is move number, say for example, 6. So we have the 6 number of moves. So encoding this Turing machine, we have to encode the 6 moves. So see how we can do this. First, what you need to learn, you have the states Q0. So HA and HR, you know the HA, here you are using the states HA, and HA is given the 0, you know that. And you are using HA and then Q0, P and R. So HR, if your machine is going to crash, then you will have the HR, and it is double 0, and Q0 assuming that it is the Q1, Q2, Q3 like this. So this will receive, Q0 will receive 3 zeros, okay, and P, you are going, why 30 here? Because you know that HR is the state HR we represent by writing the double 0. So now Q0 is associated with 30, and we say that now P you are having. So you have the P. How many zeros you will have? P 4 0. So P can be have the 4 zeros. Then R you have the 3, 4, 5 zeros. You can have the R is corresponds to the 5 zeros. Okay. So actually you are having as A. So this is 0. You are having SQ. This is okay, 000, then you are having the SP, you have the 40, and then you are having the SR, which is the, okay, so you are having the S, so you are having S and R. So this is the 5 number of 0. So we have 1, 2, 3, 4, 4 states. So one, we already know that halt state 0, Q0, 3 number of zeros. Say for simplicity you can also write like 3, 0, 3. Or, and this you have the 4 number of 0, you can say 0, 4. And you can have the 5 number of 0, 3, 0, 4, 0, 5, 0. Okay, so R is of having the 5, 0. 0, 5, and this have only the single 0. So this is the state name, and you have the two symbols A and B. So we have the blank, you know that, and blank we have the 0. Okay, and now we have the other symbol, which is, say, A. We can give A as the 00, and you have the B, and B can be given as 000. So we have the two tape symbols here. One is A and other one is B. So, and we have already learned that blank symbols we are going to assign 0, and from every AI we are going to assign the 0 I plus 1. So okay, so here tape symbol A can be given 00, tape symbol B given 000. Yes. So this we have given. Now direction, we know, with direction already we have, and so direction is stationary, we have single 0, and we have the L, which is the 00, we have the R, which is the 000. So this is the direction we have already seen associated. So how we are going to encode? Here you have the initial state of this machine is Q0. So for encoding of the machine means you are going to give the encoding of the machine, Turing machine. Turing machine means you are going to obtain the strings of zeros and ones. So encoding of the Turing machine T. So here you have the, say, I can write here, I'm going to encode the Turing machine T. So for encoding of the Turing machine T, first you need to encode the, we have, you know that how we have given the encoding. Encoding of the Turing machine T is what? First you have the initial state from where your Turing machine start. So here you have the initial state is what? You have the initial state 1, and then you have the encoding of the moves. So initial state is Q0, so you can say that as Q0. Q0 is initial, and what is the Q0? Q0 is the 30. So this Q0 is corresponds to what? 30, 40, and R is what? 50 you have. So you can say 30, and I'm just writing in the short form 03. This means 3 zeros, okay? And then you are going to separate by 1. You are separating by 1. Now you have to encode the move M1 like this, and you have the move MK. So M1 is what? Assuming that this is the M1. So M1, the 5 tuple you have. So what is the first one? You have the first one is what? State. It is the Q0. So we have the 3 zeros here. Then separate by 1. Then you have the blank symbol, and blank symbol, we know that this is the 0. So we have the 0 here. Then separate by 1. Now this is the current state, and this is the symbol is scanning under head position. What is the output now? It goes to the state P, and P we are given the 4 zeros. So you have the P, and we have the 4 zeros, and separate by 1. Whenever you have the P, okay, after that we are having the tape symbol, and tape symbol is blank, we are replacing with the blank. So you have the blank, separate by 1. Then you are moving the direction of the tape is right. So for the case of the right, we have the 3 zeros. So you are writing 3 zeros and then separate by 1. Okay. Now this is the move M1 and then finally this 1. So you have the 1. So this is the end of the move 1. So from here to here you have the move 1. So this is the move, say for example M1. Now you can go for the second move. Whenever you are going for the second move, what is the state? So state name is what? So state name is P and P is for the 40. So you have the 40. This is the current state. Then what is the symbol? Tape symbol is B. So B is what? B you have associated with 000. This. Then separate by 1. So this is the current state. P. You have the tape symbol is B. Now what is the output? You are remain in the same place. Means P means 40. So 0, 4 and you are separating by 1. Then you have the tape symbol which is B and this means 000 and separate by 1. So state and this and then you are having the direction and direction is 000 R means 000. So you are having 3 and separate by 1. So this is the move. This is the move number 2 and then this move is EM2 separate by 1. Now go for the third one. The third one means what? You are in the state P and whenever you are at the P, okay, so whenever you are at the P, you have P means 4. So you are having the 4, 0, 4 separate by 1. What is the current tape symbol? Current tape symbol is A and current tape symbol is A. A means what? 00. So you have the A and 00, 02. Then separate by 1. Now this is the current state is P. Tape symbol is this. What you are doing? You are changing you are going to the state R. So R is what? 5 zeros. So you are going to the state R. So you are having the 5 0. Then what is the tape symbol you are changing? You are changing A to B. So B means 3 zeros. So you are having the 3 now. Then separate by 1. Now you are moving to tape head left. And left is corresponds to what? You are having the 2 zeros. So you have the 2 0. This is left. Okay. Now this is the move. This is the move. What? This is the move M3 and then you separate by 1. Now go for the fourth move. So you are in the state P, which is the fourth number of zeros. Separate by 1. Current symbol is what? Blank. Separate by 1. You are going to the state R. You have 5 times zeros. Then separate by 1. Tape symbol is blank. 0, 1. Then direction of the tape head is 2. IL means 2 zeros. And this is 1. So this is again, this is the move M4 and you are separating by 1. Then see, I'm writing here or you okay. From here we continue. So you can say that from this we are going. So you are going for the fifth move number 5th. So once you are having the move number 5th, then what you are having? You are in the state R means 5 number of zeros. So you have the 5 number of zeros. R means 5 times 0, separate by 1. What is the tape symbol? Tape symbol is what? B. B means you are having 3. So this is 3. Then separate by 1. So this you are move number 5th. Okay. So in move number 5th, you are in the R. Tape symbol is B. You are going to the R, means you are having the 0, 5, separate by 1. Tape symbol is what? Same. B means 3. You have the 3 zeros. Then you have the direction. The direction is what? L. L means you are moving to the left side, and hence this is the 2. And this is the move. This is move number is what? This is move number 5. Then separate by 1. Now you are going for the final move number 6. So you are in the state R, and R is means 5 0. So you have 0 5, separate by 1. Now once you are separating by 1, what is the symbol? You have the blank symbol, so you are 0. Then separate by 1. You are going to the halt state. Okay, so halt state we are going to denote by writing 0. So this is the R. From R you have the tape head symbol is blank. Then you are going to the state halt. Halt means 0. So you write single 0 here. Separate by 1. Tape symbol is again blank. Separate by 1. Direction of the tape head movement is stationary. So this means 0. Separate by 1. And hence this is the move 6. And now you are going to separate by 1. So this is now you have encoded the Turing machine. So once you have encoded the Turing machine, then you can supply. And assuming that you have that your input, you have to give the input also. So if you have the input, say input is I can say input is like, say x is equal to double BA. If you have the double BA, or you can say this is the z is equal to double BA. So how you can give the encoded? So once you are encoding the input, EZ, then you have to begin with 1. You know that. So you have to, once you are supplying the input to the universal Turing machine, then you have to place the input at the end, and since encoding form, so ET and EZ. So this is actually up to here you have the ET, then you have to give the input. So actually input is what? This is the input 1, starting from the 1. And now if input is, say for example, if z is equal to double BA, then you have this is what? So B means what? B is what? B, you have given the 3 zeros, so you are having the 3 zeros. This is then separate by 1. Then again B, how many? 3 zeros, separate by 1. Then A means 2 0, and then separate by 1. So now this is what? This is actually the input. This is the input, and say this input is z, and z is equal to what? Double BA. BBA. Okay, so BBA. This is the input. Now this is, so what you have now, this the Turing machine is universal Turing machine is given the input now like this. So you have the ET and EZ. This, so ET and EZ. So this is the input actually. So for once you have the universal Turing machine, so the universal Turing machine is given the input this. So you are supplying this input to the universal Turing machine, TU, and this is the input. And then finally your Turing machine TU is going to simulate the move of t on the input this using the transition of the t. So from M1, M2, M3, M4, M5, M6, since you have the 6 number of moves, so here this is what? This is the ET, this is the ET starting from this, and now this is the EZ. So your universal Turing machine is given the encoding like this. So this is the composite string of zeros and ones, and this is this machine. If you supply this machine to the universal Turing machine, then you have to encode according to the encoding scheme we have discussed. And in this encoding scheme, this is the way you can encode this Turing machine. And finally, your universal Turing machine is supplied this input. So this is the string of zeros and ones. Now you may have questioned that how universal Turing machine now can simulate the action. So universal Turing machine can simulate the action, and means you have to you can think that how we can design the universal Turing machine. So how you can design the universal Turing machine so that it can take the encoded form of the some Turing machine along with the input you are going to supply, and then it processes the input on the by the given Turing machine. So for you can design the Turing machine TU using the 3 tape. So you can use the 3 tapes. 3 tapes TU can be designed, can be constructed. Your universal Turing machine TU can be constructed using 3 tapes. 3 tapes. So we can use 3 tape Turing machine. Means you can have 3 tape Turing machine. We can have the 3 tape Turing machine. Universal Turing machine can be constructed using 3 tapes, and this aspect you can achieve the goal using the 3 tapes. So how you can do actually? So once your Turing machine is supplied the input, which is the string of zeros, how your 3 tape Turing machine, which is the universal Turing machine, how it can identify. So you have the 3 tapes here actually, tape 1, or you can, okay. So you have the tape 1, then you have the tape 2, if you are constructing tape 2, and then you have the tape 3. So, okay. So tape, you can say tape 0 or tape 1, tape 0, tape 1, and this is tape 2. So you have the 3 tapes for designing the universal Turing machine. So universal Turing machine. So universal Turing machines can be designed, TU can be designed using the 3 tapes. So what is the purpose of 3 tapes? So again you have the tapes which are the squared, same, okay. So at the beginning you are giving the input, and this is the input tape. Tape 0 is actually the means first tape is actually the input tape. So this is the input tape. Means at the beginning, whatever be the input, it is stored in the tape 0. And tape 0, once you supply, this is the input to the universal Turing machine. This is the input. So encoded form means you are going to give the encoded form of the Turing machine ETEZ. This is the input, and this input is stored in the tape 0. So see, once how universal Turing machine then process, then this whatever be the output actually, and output will also store in the tape 0, means tape 1, which is tape 0. So also this is the output tape. So tape 0 is also the output tape, and tape 0 is also the input tape, which contains the input like this. Now during the simulation of moves, what universal Turing machine should do, actually you know that at the beginning of the encoding form of the ET, we have the initial state. Okay, so initial state, that is the current state. So from this beginning, actually your universal Turing machine, so the first job of your universal Turing machine is to take the current state, identifies the current state, and it knows that the current state will be at the beginning of the encoded form of the Turing machine. So from that starting zeros, then here you have the number of zeros, and means tape 2 means tape 0, tape 1, this is the tape 2, means this is the tape 3. So for the simplicity, actually, instead of writing 0, 1, you can just write 1, 2, and 3. So tape 1. So tape 1 is acting as the input tape. Tape 1 is also acting as the output tape. Tape 3 is used for storing the current state. So it is the encoded, it holds the encoded form of the current state. So whatever is the current state, you are writing here. So universal Turing machine knows that, okay, from here is the current state. So from the beginning of the encoder from the Turing machine, it copies the state till it finds the 1, as you have the till it finds the 1, and it is stored in the tape 3. So tape 3 is used for storing the current state of the universal Turing machine, current state of the input Turing machine actually. So tape 3 is used for this, and tape 2 is used as the working tape. This is the working tape. So working tape, this is the working tape. So we have the tape 2, which is used as the working tape, means during the simulation of the move of the T, you are using this tape. So what you can do in this tape, you can use the, say for example, this tape 2 can hold the, if you identify, tape 2 can hold the tape symbols. Okay, so during the execution, you are simulating the moves, you are going to process, and you are modifying the tape symbols. You may delete some tape symbol. So tape 2 is generally used for the working tape. So once you go for the universal Turing machine with the 3 tape, then generally tape 1 is acting as the input tape, tape 1 is also acting as the output tape, and tape 2 is the working tape during the simulation of the moves, and tape 3 is generally used for keeping the encoded form of the current state of the input Turing machine. Now, how actually Turing machine is going to, how universal Turing machine TU will simulate the moves, simulate the execution of the Turing machine T, which is supplied in the encoded form. So first job is to what? On behalf of the current state and on behalf of the current symbol, you know that move consists of the 5 tuples, and first one is the state, second one is the tape symbol. So state and tape symbol. So first, how you have to, your universal Turing machine is going to identify the moves, because it knows that moves can be of any order. You may store the first move at the last, or any order, you have the any order. So the first job of the universal Turing machine is to find the pattern. So actually at the beginning, your universal Turing machine is doing the pattern matching job, and first it identifies the pattern, means what pattern it is going to match, the state and tape. So you have the state, and then you have the tape symbol. Once it has to match on this. So in the move 1, it says that whether it is the current state is same. Yes. If it is same, then is the tape symbol is same. Yes. If it is same, then it identifies that okay, yes, this is the move. Otherwise, it skip everything and it goes for the next move. Again, it finds what is the state, what is the tape symbol. So on behalf of the two tuples, it is going to identify the moves of the input Turing machine. So once your universal Turing machine is identifies the move, then it wants to know that what is the output of this move. So whenever you have identified the correct move, then next three tuple of the move is actually the output produced by the transition function. So say for example, if your Turing machine identifies that okay, yes, this M1 is the correct move for this current state, then it needs that okay, what is the output of this transition function, and output is what? It is in the state 04. So this is the state name, and this will become the current state, and this current state is copied to the tape 3. Now this tape 3 will hold this current state. So tape 3 always holds the current state. Then you have the symbol, tape symbol, and you modify the tape symbol here in the working tape. And then you find the direction of my move. So once you are moving the tape head to the left side, right side, accordingly you are moving to the input. So you are moving to the tape symbols to the left side or right side. Once it is done, then again you have the current state and current tape symbols. Accordingly you will search the moves, and once you search the move, you find what is the value of the move. Accordingly you again modify the current state of the machine, current state, and your tape symbol you are going to modify. And this is the way. So your Turing machine, universal Turing machine, first your universal Turing machine is going to do the pattern matching job. And for in this pattern matching, once it identifies the correct moves, then it finds the what is the output of the move, means what is the output of the transition function, and hence then it is going to find out the output, and accordingly it is going to modify the tape 3, and also it is going to modify the tape 2. So this is the simplest, this is one way, and this is some brief description about the universal Turing machine. We understand the behavior of universal Turing machine just like our computer. Our computer can execute several algorithms. In the same times, we have designed the universal Turing machine, and that universal Turing machine can be given input to any Turing machine along with the input that take. And it can simulate the action of the input Turing machine along with the input. So this is just the simulation of the modern computer.